Hello and welcome everyone to the April's edition of ThalesNano's webinar series. My name is Nandor Kanya and I am an application scientist of the ThalesNano team. And today I would like to talk a little bit about continuous flow hydrogenations for you and have a look at some of the advantages that these instruments that can perform continuous flow hydrogenations have compared to batch processes. So first of all, let me give you a brief outline about today's webinar. It will be sectioned into 4 pieces. First of all, we are going to talk about the comparison between traditional batch hydrogenations and flow hydrogenation techniques, and have a look at some of the advantages that the flow technologies might have versus the batch processes. And then during the second section, I'm going to briefly introduce to you all the ThalesNano instruments that is capable of performing continuous flow hydrogenations with the main focus on the H-Cube series. And then during the third section, I'm going to focus on the H-Genie platform, which is another instrument from ThalesNano that is capable of doing continuous flow hydrogenations. And we will have a look at the main advantages that this system has. And then finally, over the course of the fourth section, I'm going to give you a few experimental and chemical examples that have been performed in the H-Genie platform, and we'll have a look at how this instrument has a few advantages compared to either batch or other flow chemistry techniques. So during the first section, I'm going to talk about the comparison between batch and flow hydrogenation techniques. And first of all, let me give you some of the problems that the traditional batch hydrogenations might have. So the first problem is of course the hydrogen source. Because if you are doing a traditional batch hydrogenation reaction, you have to use a hydrogen cylinder, which is a highly dangerous task. It is normally required to be a trained personnel, so not everyone is capable of using hydrogen cylinders, and oftentimes it must be kept separately, it must be stored separately from the lab environment, and the transportation of the gas itself can often be difficult in the laboratory. And then, of course, there's the problem of fire hazard and explosion of risk, because, of course, hydrogen is a highly flammable gas. So it is extremely dangerous in the lab environment to use. The explosion threshold of hydrogen is very low, so even only a few % of hydrogen concentration mixed together with the air is already forming a flammable mixture or an explosive mixture, and therefore it is highly dangerous to handle these kind of experiments. Hydrogenations often require catalyst, which can be pyrophoric, and if it comes into contact with the hydrogen, it can instantly ignite or even explode, and oftentimes the catalysts themselves, when they contact with the air, can catch fire. So we are talking about an extremely dangerous process. The scale-up of traditional batch hydrogenations can also be challenging because the risks involved with the scale-up increases with size, and the reaction times can also be quite tedious and quite long. If we are lucky and we have an easy experiment, it can be only a couple of minutes to a couple of hours, but for more difficult hydrogenations, it can take up to a couple of days to perform a full conversion. So here we can see on this slide a summary of the hazards of all the batch hydrogenation techniques. Of course, it doesn't need to be pressurized, but some people use pressurized cylinders to perform these reactions, and therefore the release of hydrogen is always a danger. It mixes then together with the air and form an explosive mixture, and that is of course a highly dangerous circumstance. During batch hydrogenations, it is required that the user, the chemist, handles the catalyst, which can be again pyrophoric. So that's another source of danger. And of course, the solvents that are often used for hydrogenations, for example, methanol and ethyl acetate, these are highly flammable liquids, so it only serves to increase the dangers of the hydrogenation process. Also, let me give you the idea that the major issue with the scale-up is that if you scale up a batch hydrogenation technique, the hazards actually increase with the volume. Whereas if you are trying to scale up the continuous flow hydrogenation technique, the scaling up actually becomes more safe as opposed to more dangerous. But we will have a look at that in detail in a later slide. So how can the flow hydrogenation technique reduce or even completely avoid all of these risks? So first of all, in continuous flow hydrogenations, you have a reduced amount of hydrogen that is constantly present in your reaction mixture. So we are basically decreasing the amount of stored gas in the reaction environment. Because of course, in batch, you have all of your desired materials, all of the products that you wish to convert into the hydrogenated product, those are all present at the same time in the same flask. Whereas in continuous flow techniques, you are only reacting only a very few percentage of your desired amount of material at any given time. So even if something does go wrong, you are only losing a very small fraction of your valuable materials, and also only a very small fraction of the hydrogen gas is present inside the reactor zone, so therefore the risks are greatly reduced. One solution that is often used in continuous flow hydrogenations is on-demand hydrogen generation. So it is a very good idea to replace the hydrogen gas cylinders with gas generators. And the main advantage of that is, first of all, you don't get to store the hydrogen, which is of course already a very big advantage, because the hydrogen storage is, as we saw in the first slide, is very difficult. But also, you are only generating your necessary amount of hydrogen and nothing more. So it can be fine-tuned and adjusted such that only your necessary amount of hydrogen, or only a very small excess of necessary hydrogen, is produced at any given time. In flow, the catalyst handling also becomes a little bit easier, because you can purchase pre-filled columns that already contain the catalyst for you. So the reaction time and the catalyst handling time can be separated from each other. So it's no longer a case of the chemist having to fill the catalyst inside their reaction zone anymore, because that can be done preemptively by catalyst experts, and you can purchase these columns and just include them into your flow line, and therefore completely avoid catalyst handling at all. Of course, in continuous flow, you have a minimized reaction volume, so only a very small amount of your reaction mixture is going through the column at any given time. So that's of course another advantage compared to batch, because smaller amounts of material present in your reaction zone will always be a lot safer because of the reduced amount of hydrogen. So here you can see some of the attributes of continuous flow hydrogenations. I have already mentioned the on-demand hydrogen production, which is of course very useful. The main technique that people use for on-demand hydrogen production is the electrolysis of water. So it's a very simple, it's a technique that has been known for centuries now. But to apply it in continuous flow hydrogenations, it's actually not that old idea. Only a couple of decades ago have this been invented, and ThalesNano is the market-leading company for flow continuous hydrogenations because of the unique technologies and patented technologies that our instruments have for both hydrogen generation and catalyst handling. So the main advantage of this is, of course, that you do not need to store hydrogen gas externally, for example, in a cylinder. And that comes, of course, with improved safety. So avoiding the hydrogen cylinders will mitigate all kinds of risks for you in terms of both catalyst handling and also forming an explosive mixture with the air is also avoided. Hydrogen leakages are no longer a problem. Pressurized cylinders are no longer a problem. And therefore it becomes much more convenient to perform hydrogenations in flow compared to batch. All of the instruments that is capable of performing continuous flow hydrogenations, they are all equipped with built-in safety features. For example, hydrogen leak detection is something that all of our instruments are armed with. And this hydrogen leak detector will automatically stop the instrument if they detect any hydrogen leakage around its atmosphere. For example, in a fume hood, if they detect a hydrogen to be present in the fume hood, it will automatically stop. They are also equipped with overpressure protection. So at various places throughout our instruments, there are pressure sensors. And if any of these sensors detect an overpressure, which exceeds the allowed amount of pressure, again, all of the devices will be automatically shut down and the hydrogen production will be automatically stopped. So the advantages of these technologies or these techniques is that the electrolysis of water provides or produces a really high quality hydrogen gas. It is at least 99.99% pure hydrogen gas that can be produced, and the pressure can also go up to 100 bars, which is really comparable to the batch techniques, because of course a hydrogen cylinder is around that regime as well. There's another advantages in flow techniques, which is that you get an improved mixing, and the heat transfer also becomes very easy because of the stainless steel tubing that we use in our instruments. It is of course a very efficient conductor of heat, and because of the diameter of the tubes, the mixing is also very fast. It happens in the first few centimeters of the two lines joining together. All of these experiments have been proven to be fast and reproducible, so all of the reactions can be really easy to reproduce and replicate. And all of the control of the parameters are also very easy because you have a user-friendly interface. All of the devices can be operated either through a common computer or using their individual buttons, and they are all really easy to learn and they are very user-friendly. So it becomes a lot easier to operate these machines compared to the batch techniques, which requires really highly trained personnel. So let me give you a little bit of idea about the on-demand hydrogen generation, which is of course performed by the electrolysis of water. So all of the ThalesNano instruments that uses this technique comes with the patented electrolysis cell technology. So here on the left-hand side of this slide, you can see one of the electrolysis cells that are unique to ThalesNano. Of course, the electrolysis itself is not new. It's a very old idea. People have been doing water electrolysis for years, but it's the geometry and the technology of the cell itself that allows a very high purity hydrogen gas to be produced, and also only a very small amount of hydrogen is required to be stored inside the cell. And also this technology allows you to not store hydrogen outside the cell. So it is very important to emphasize that the only place in which hydrogen is stored is inside the cell. And that makes the technology extremely safe. So let me move on to the second section of this webinar, which I'm going to give you a brief demonstration or brief introduction about ThalesNano's instruments for continuous flow hydrogenation techniques. So here you can see the overview of all of the hydrogenation platforms that ThalesNano offers. First of all, we have the H-Cube Mini Plus, which is the simplest instrument for hydrogenations. It is extremely user-friendly, it's very compact, and it's extremely easy and straightforward to learn. We recommend these instruments for simple experiments for introduction to hydrogenations or for reactions that are known to proceed very simply. For example, nitro group reductions are an experiment that can be very easily performed. And secondly, we have the H-Cube Pro instrument, which is a slightly more advanced version of the Mini Plus. The main advantages of this instrument is that it's modular, so you can join several other instruments and connect the flow line into the H-Cube Pro of several different instruments. It comes with an adjustable amount of hydrogen that is produced, and it allows you to perform more advanced or more difficult chemistry compared to the Mini Plus. And finally, we have the H-Genie platform, which is basically a scale-up of the continuous flow hydrogenations. It is also modular, so you can connect all kinds of different flow chemistry equipments into this system. And also scale-up becomes really easy with this instrument, but I am going to demonstrate the Phoenix H-Genie system in a lot more detail in the upcoming slides. And of course, the main advantage of this series and the reason why this is an unprecedented equipment on the market is they combine on-demand hydrogen generations and continuous flow hydrogenation in one system. So not only are you performing the reactions in continuous flow mode, which is a lot more safe than batch, but also you are also generating the hydrogen gas in situ, which makes the design inherently more safe and more convenient. And that's why the ThalesNano instruments are sort of market leaders, or you know, this is an unprecedented technique that nobody else has on the market. So before I move on to the Phoenix and the H-Genie platform, let me give you a brief comparison between the H-Cube Mini Plus and the H-Cube Pro, which is sort of the smaller scale or medium scale hydrogenation instruments of ThalesNano. The Mini Plus is of course the simpler system out of the two of them. It produces about 25 normal milliliters per minute of hydrogen gas, and the temperature range goes up to room temperature to 100 degrees centigrade. And it is a really user-friendly instrument because it includes guides and videos. If you turn up the screen and turn on the instruments, there's a button on the screen which will allow you to choose from several different tutorials and videos, and those will make your life a whole lot easier for doing experiments. It will be explained how to set up an experiment, how to set up the flow line itself, what happens if the system gets blockaded, or what happens if the hydrogen gas is leaking out of the system. All of these questions are answered for you in these videos and guides. It is really a perfect system for beginners, for very easy hydrogenations, for educational purposes as well. And it performs entry-level hydrogenations that are known to proceed easily, very conveniently. And then we have on the right-hand side, we have the H-Cube Pro, which is a slightly more complex hydrogenation system. You can see that the amount of hydrogen is more than double compared to the H-Cube Mini Plus. It is now capable of doing 60 normal milliliters per minute of hydrogen gas. And it comes with adjustable hydrogen amount. So You can decide whether you would like to use the full 60 milliliters per minute, or you can set it up to 40 or 30 or whichever amount you would like. It is also equipped with a bubble detector, which is an extra safety feature, so to speak, because it will tell you if the hydrogen is flowing inside the system or not. The parameter space have been slightly extended from 10 degrees to 150, so it is also capable of cooling, and the heating is also has been extended to 150 degrees C, and it is also equipped with a back pressure sensor and also a simplex method, which allows you to do optimizations very easily and in an automated way. So simplex is just a mathematical or statistical technique for optimizations that will allow you to find the optimum of your reaction conditions a lot more easily compared to if you are doing it by hand. This is an automated method that will do it for you. So this instrument allows you to do more advanced and also more difficult chemistry. During the next few slides, I would like to take a few moments to tell you about heterogeneous catalysis in flow, because it is a really important and also very interesting topic. So the way that you are doing hydrogenations in flow is to load a column with a catalyst, or that's one of the main techniques that people do it. And the most common catalysts are, of course, palladium on carbon or platinum on carbon, or Rene nickel are just a few examples that are the most commonly used catalysts, heterogeneous catalysts in flow. These catalysts can be loaded into metal columns. And this can be done either by the user, but also you can order pre-filled catalyst cartridges or columns, and therefore you can entirely avoid catalyst handling all by itself. And the main advantage of this technique is that the columns itself are equipped with filters on both ends. So if you purchase a pre-filled catalyst column, the catalyst will be sort of trapped inside, and you don't have to worry about filtering the catalyst because all of the catalyst columns are equipped with filters on both ends. So if you connect them into your flow line, only the liquid and the gas will be able to come through, but not the solid catalyst itself. So this is another advantage compared to batch hydrogenations, because in batch you need a workup, you need a filtration step to be included in your downstream workup procedure, whereas in continuous flow hydrogenations, the catalyst filtration is sort of automatically performed by the system itself, so you are only getting your solution of the product to exit on the end of your flow line. Most often times, the only thing that you need to perform is the evaporation of the solvent, and that will often give you a purity of over 95% of your desired material, desired product. These catalyst cartridges come in different sizes, and it can be filled with different types of catalysts, of course. And you can check on the ThalesNano website about the different sizes and the different catalyst cartridges that we offer for you. These cartridges are compatible with both the H-Cube series and also the H-Genie platform, which I'm going to talk about a little bit later. So here we have an example of the so-called metal sealed, or otherwise known as MMS for short, cartridges. These are also these also come with all sorts of different sizes and can also be equipped with different types of catalysts, and they can withstand a temperature of even 450 degrees centigrade. So it allows you to do even extremely difficult hydrogenations, such as, for example, the aromatization of benzene rings is a reaction that that is known to perform a little bit more difficultly than just functional group transformations. So these are the sort of columns that you can equip into the Phoenix flow reactor for scale-up purposes. They can be reused countless of times. They can be refilled. Once the catalyst has been depleted, it can be discarded and filled again and used many times over. The length, of course, and the inner diameter can also be varied. So you can choose the correct size of your catalyst bed compared to your experiments. So you can always adjust the size of your instruments to your chemistry and to your scale. So next, I will talk you through the Phoenix and the H-Genie platform. How can these instruments be used together for continuous flow hydrogenation techniques? So here, first of all, let me give you a brief introduction to the Phoenix flow reactor. It can achieve a temperature of up to 450 degrees C and up to 200 bars of pressure, which is the maximum capability of this instrument. However, it is important to emphasize that if you are using a gas-liquid mixture, then the maximum limitation of this instrument becomes actually 100 bars. However, 450 degrees C combined with the 100 bars of pressure is already quite a harsh condition, so it will enable you to do very difficult chemical reactions easily. The Phoenix instrument can be equipped with either heterogeneous or homogeneous reactions, and it can handle either liquid-liquid mixtures or gas-liquid mixtures. So there's a very wide window of chemical experiments that can be performed in this system. The reactor zone can also be made out of several different materials. PTFE is very good for lower temperature experiments, and then stainless steel or Hastelloy reactions are the ones that can withstand a couple of 100 degrees centigrade in temperature. And it can be coiled into loops, and therefore you can determine the residence time by deciding how long of a coil you would like to make out of these steel or Hastelloy lines or tubes. And also the Phoenix can be equipped with cat cards and MIDI cards, which are ThalesNano's solutions for heterogeneous flow hydrogenations. These are basically just catalyst cartridges that I have mentioned on the earlier slides. The Hastelloy version is an advantage when you are doing reactions with corrosive materials. For example, nitric acid is a common example that people mention that require Hastelloy instruments, and also ammonia reactions sometimes require the presence of ammonia. We will see one example later during these slides that require the use of ammonia and therefore a Hastelloy instrument. Because we are using stainless steel or Hastelloy tubings, the heating is extremely rapid. Only a couple of seconds of residence time is enough to achieve 90 to 95% of your desired end temperature. All of the ThalesNano instruments have built-in safety features, so let me briefly go through them for the Phoenix reactor as well. I think the most important property is that the reactor door must be kept closed in order for the instrument to start heating. So if the reactor door is open, you cannot even start the heating procedure. And also, when the heating is started and you accidentally open the door or intentionally open the door for that matter, the heating will automatically stop. So even if you finish your experiment and forget to turn off the heating and open the door, the heating will be automatically stopped for you. The Phoenix flow reactor is equipped with a pressure release valve, so it is automatically set to a certain pressure value, which if it is exceeded, it will release the excess pressure into the fume hood, and therefore it is granted that the instrument never functions anywhere above its desired or allowed pressure range. The instrument is also equipped with a temperature alarm, so it is really easy to avoid overheating because you get an error message, and it also stops heating if that happens. And we also supply a heat exchanger unit for the Phoenix flow reactor, which is of course very useful to cool down the outcoming line to avoid, touching it by the user. So if the user accidentally touches the stainless steel wire that is exiting the reactor, we can avoid burning injuries by the heat exchanger. Next, I would like to talk about the H-Genie hydrogen generator unit, which is a sort of the pair of the Phoenix flow reactor in order to perform continuous flow hydrogenations. It is a hydrogen generator that uses the electrolysis of water to generate hydrogen gas on demand. Of course, the electrolysis also produces oxygen gas, but oxygen is released into the fume hood on the top of the device. So it is never mixed together, it's never injected into the flow line, and therefore it never has a chance to mix together with the hydrogen that is being produced. And the oxygen outlet and the hydrogen outlet are separated in space, so that this is an extra safety feature so that these two gases never have a chance to mix together. The Genie can go up to hydrogen production of maximum 1000 normal milliliters per minute, and it is capable of reaching up to 100 bars of pressure. These are really good values for continuous flow hydrogenations because it will allow you to both scale up your experiments really easily. So 1000 milliliters per minute can be considered to be a really high amount of hydrogen per minute. And the 100 bars will allow you to perform very difficult chemistry as well. The purity of the hydrogen that is being produced is at least 99.99% guaranteed. However, with a so-called dry cart, which is an extra add-on to the H-Genie, you can actually achieve 6.0 purity. So that means 99.9999% purity of the hydrogen gas. The water tank of the H-Genie unit is 3 liters, and it's consuming at full capacity about 0.2 liters per minute, liters per hour of water. So it can easily go for a full day of an 8-hour shift without actually much intervention from the user. The Genie is compatible with a lot of the ThalesNano instruments, and it can also do batch and flow reactions, so it can easily fill a reaction mixture for you with hydrogen, including round bottom flasks or autoclaves or even balloons, or the hydrogen gas that is produced can be ejected into the flow line and therefore be able to perform continuous flow hydrogenations. The interface of the H-Genie is actually really simple. The setup is very easy and user-friendly. Basically, you just have to plug in everything and turn on the instruments, and it's ready to work for you. It comes with 3 modes, as you can see on the right side of this picture. It has a batch or a flow or a balloon mode, and all of these modes will allow you to set up your gas flow rate and the pressure of the hydrogen gas that you desire to use. There's a computer equipped in the H-Genie that will monitor the hydrogen consumption, and it will record all of these data, and these can be saved to an external USB stick, for example, that can be loaded into your computer, and therefore the data can be saved and analyzed for later purposes. For example, reaction optimizations. You can read the data even long after you have finished your experiments. The main purpose of the H-Genie unit is to replace hydrogen cylinders. So instead of purchasing hydrogen cylinders, which contains thousands of liters of hydrogen gas, and you have to store that hydrogen gas, Instead of that, we are producing hydrogen gas on demand for you, and the maximum amount of hydrogen that is being stored inside the Genie is actually only 150 milliliters. And it is entirely contained within its electrolysis cell. You can see in the safety features. So if you see that the second point of the safety features declares that. And this makes this entire design to be inherently safe. And of course, again, we have some safety features to discuss that comes with the H-Genie. For example, it is also equipped with an internal hydrogen detector, so if there's a leakage of hydrogen gas, and therefore the hydrogen appears in the atmosphere of the fume hood, the detector will go off and it will notice this and perform an emergency shutdown. So if hydrogen is detected anywhere around the Genie, it will stop producing hydrogen on its own automatically. We have mentioned the contained hydrogen, so a maximum of 150 milliliters of hydrogen gas is being stored at the instrument at any given time. So you don't need to store hydrogen in large amounts. The water tank is also equipped with a water level sensor, which will give you a warning way before you run out of hydrogen. So even if the warning does appear, the device is capable of functioning for several more hours before it will stop. It is also equipped with an overpressure protection, which will automatically stop the instruments in case it detects a blockage. So how can the Phoenix and the Genie be used together to perform continuous flow hydrogenations? Here you can see the two instruments and also several other modular devices that can be included in the flow line, and also a schematic representation of one possible arrangement of these devices. So on the upper picture you can see three more devices that I haven't mentioned yet. From left to right, they are the control module, which is basically just a computer that allows you to control all of the other instruments at the same time. Next, we have the pressure module, which is essentially just a back pressure regulator, which creates a resistance against the flow of the liquids or fluids, and therefore it allows you to build pressure inside the system. And then in the middle, you can see the gas module, which is essentially just a mass flow controller for gases. It allows you to set up, it has 14 different gases programmed into it. So if you would like to use some other gases than just hydrogen, then the gas module will allow you to do that. And it will allow you to regulate the amount of the gas that you would like to use, and regulate the amount by adjusting its flow rate. So on the bottom of this picture you can see the schematic representation of a flow chemistry system that is equipped with the Phoenix and the Genie together. So let me give you a brief walkthrough on how that works. The number one on this scheme is actually the H-Genie, so that's where we produce hydrogen. And the number two is the gas module, which is also optional. You don't have to include that instrument if you are only using hydrogen gas. But for example, if you would like to perform carbon dioxide hydrogenations to form formic acid or methanol synthesis, then you need two different gases, the hydrogen and the carbon dioxide. The hydrogen is coming from the number one, the H-Genie, and then carbon dioxide can be introduced from a cylinder through the gas module. And you can see on the picture that they meet at a mixer unit, and they are injected to the gas liquid mixture, which is labeled number 6 on this scheme. And also the pump will pump your liquid, which is labeled with number 5. So the liquid is coming from number 5 and the gas mixture is coming from 1 and 2, and they are mixed together inside the gas liquid mixture mixer, and then they are injected into the Phoenix flow reactor, which is labeled number 7. The gray parts are the heating mantles, and in the middle, using the black color, we can see the catalyst column. So it is equipped with the catalyst column itself. And then we have the heat exchanger labeled number 8. It is always optional to include that in your flow line. And then we go into number 9, which is the pressure module. Again, it is equipped with a pressure sensor and a back pressure moderator, which allows you to build a pressure of up to 200 bars for liquids and 100 bars for gas-liquid mixtures. The only instruments that I haven't mentioned on this screen are number 3 and 4. So these are just the control module itself, which is the brain of this whole system, and the number 4 is just a communication interface that allows you to plug together all of these instruments and allow the control module to control all of these instruments at the same time. And finally, let me move on to the final section of today's webinar, which is going to be a little bit of chemistry. We are going to take a look at several chemical equations or reaction equations that were performed in either the H-cube or the Phoenix-Genie system, and we are going to compare them together and see the advantages of the Phoenix-Genie system itself. So first of all, the first example is going to be a nitrile group reduction to form a primary amine. This kind of experiment has been performed in both the H-Cube Pro system and also the Phoenix-Genie system that you have just seen on the previous slide. And you can see that if you are using an H-Cube Pro, then the maximum amount of hydrogen is 60 milliliters per minute. And that was actually not enough for this starting material, this nitrile, to fully convert into the primary amine selectively. And therefore we had to use the addition of ammonia, which requires Hastelloy instruments because it's a corrosive mixture and it is quite unpleasant to work with. So using the ammonia, we were able to selectively perform the synthesis of the primary amine, but of course, the ammonia is, when the ammonia is required, it becomes a lot less convenient. And switching this experiment into the Phoenix-Genie system allowed us to completely avoid the use of ammonia by increasing the amount of hydrogen. So the H-Cube Pro only allows 60 milliliters per minute of hydrogen. With the Phoenix-Genie system, you can go all the way up to 1,000. And it turned out that even only doubling the amount of hydrogen gas to 120 normal milliliters per minute is already sufficient to avoid the use of ammonia altogether. So you no longer need the unpleasant corrosive mixtures. It becomes a lot more convenient. And I forgot to mention that we were using the same concentration of starting materials. So both of these experiments, both in the case of H-Cube Pro and the Phoenix-Genie, we were using 0.05 moles per liter solutions. And you can see at the bottom of this slide that using the Phoenix-Genie system, 97% selectivity could be achieved for the desired primary amines. So the Phoenix-Genie system allowed us to avoid the use of the corrosive mixture altogether by increasing the hydrogen amount or the excess of hydrogen. The next experiment that I would like to briefly talk about is the saturation of heteroaromatic rings. This experiment was also performed in 2 different instruments, the H-Cube Pro and the Phoenix-Genie. And in this case, it was our observation that the Phoenix-Genie allowed us to reach 2 different optimums. Because you can see on the left-hand side that the H-Cube Pro can only go up to 150 degrees centigrade. And therefore, we had to apply a little bit higher pressures, and we had to use a little bit more potent catalysts because of this temperature limitation. So it is true that we only applied 90 and 80% degrees during this experiment, but we had to use 60 to 70 bars of pressure and a 10% palladium to achieve acceptable conversion rate. So this lower temperature option allowed us this conversion to be possible, but the only way to do it was to use really high pressures and really potent catalysts. Meanwhile, in the HGenie system, which is capable of achieving 450 degrees C, this extended scope of parameters allowed us to reach a different optimum. So of course it is possible to just replicate the previous synthesis using 80 to 90 degrees and 60 to 70 bars of pressure, but we wanted to extend this scope of parameters and look for a different optimum which uses high temperatures as opposed to high pressures. And we were able to do that, achieving 200 degrees C at 35 to 40 bars, which already allowed us to even achieve better, in some cases better conversion rates compared to the HQ Pro, and also the amount of palladium could be reduced to 5%. So it allows us to use cheaper catalysts and also allows us the choice. Do we like to use more higher temperatures or higher pressures? Both of those options are available in the HGenie system, while with the HQ Pro, a high temperature option was not available. We had to resort to the high pressure option. So that is, of course, another advantage that the HGenie might have for continuous flow hydrogenations. It gives you more options. It extends the parameter space such that you are allowed to choose from several different optimums according to your needs. The next reaction is going to be a one-pot synthesis in which we would like to reduce a nitro group into an amino group as well as saturate a heteroaromatic ring. And this was a really interesting experiment because we have found two different optimums for this reaction. Because if you are using a slightly less harsh conditions, namely 60 degrees C and about 10 to 15 bars of pressure, it is actually possible to stop at the nitro group reduction. So if you do not wish to saturate the aromatic ring, it is possible by using slightly less harsh conditions. And the main product, this aminoquinoline derivative, could be isolated at 98% purity. And we have detected that the side product is only 1.5%, and it's actually the ring saturated product. And it turns out that the 40 degrees and the 10 bar option yielded a slightly different result with a slightly less conversion and only a different side product. So we managed to isolate the N-hydroxy derivative of the amine with a 5% yield. And at that point, we started to increase the temperatures and pressures and also the flow rate of the hydrogen. And we have observed that the amount of ring-saturated product started to increase. And we have managed to find the optimum. This is experiment number 7, which is the optimum conditions for the amino tetrahydroquinoline derivative. It turned out to be 160 degrees and 45 bars using 120 milliliters per minute of hydrogen flow. This experiment turned out to be really yielding. More than 99% selectivity was achieved, and quantitative conversion was also achieved in this experiment. And we can immediately see the advantage of the HGenie system, because this experiment was performed in the HGenie system using a 0.05 moles per liter concentration of the nitroquinoline starting material, we can immediately see that the full one-pot reaction would not have been possible in the H-cube system, because we are using 120 milliliters of nitrogen, and also we are using 160 degrees C, which is slightly above the maximum allowance of the H-cube Pro. And the hydrogen amount is actually double compared to the H-cube Pro. So that means if we would like to transfer this experiment back into the H-cube Pro, we would have to halve the concentration of the starting nitro compound to achieve a similar result to this. And then finally, this is going to be our last example. I would like to give you a demonstration on how the H-Genie instrument makes scale-up really easy. So first of all, I'll describe an experiment that was done in the H-cube MIDI instrument, which is a device that is no longer in circulation. So we have stopped the production of the H-cube MIDIs a while ago. But a couple of years ago, we have performed a scale-up synthesis using the H-cube MIDI. We have used a 0.1 molar concentration solution of methyl paranitrobenzoate solution, and we have been pumping that solution at 10 milliliters per minute and using 100 milliliters per minute of hydrogen flow rate and a so-called MIDI cart, which is a catalyst column. We have been able to achieve 8.7 grams of the amino product per hour at about 90% isolated yield and 98% selectivity or 98% purity. And then recently we have transferred this reaction into the H-Genie system, and the main purpose of this experiment was to increase the throughput tenfold. So you can see that the colored conditions have been increased by a factor of 10. So we have used the same solution, 0.1 moles of methyl paranitrobenzoate, but the flow rate has been increased by a factor of 10 to 100 milliliters per minute. And also using the Genie, we have been able to increase the hydrogen flow rate all the way up to 1,000 milliliters per minute. We have kept the conditions to be the same, so temperature is the same, and pressure, and also the catalyst was also the same in both of these cases, except the catalyst column, a larger MMS catalyst column was used. So the difference between the MIDI cart and the 1-inch MMS column is about 8 to 10 times, so 8 to 10-fold. So the MMS column can hold about 8 to 10 times as much catalyst as the MIDI cart. And the results of these experiments was that after about 4 hours of reaction time, the conversion rate started to drop below 95%. And in order to avoid a low conversion, we at that point decreased the flow rate of the liquid to 80 milliliters per minute. And by doing that, we have been able to maintain the conversion rate above 95% all the time. This reaction have been ongoing for 7.5 hours, and the overall purity of the combined products was maintained above 89%. So it's essentially the same result as in the case of the MIDI. And you can see that the average throughput, if you take the average of the 100 milliliters per minute time and the 80 milliliters per minute time, you take the average of those, you get about 83 grams of product per hour. After some calculations, of course, you have to do the conversions of moles into grams. But after those calculations have been done, we have determined that the average throughput of this system was 83 grams of the benzoate, which is about 10 times as much as in the case of the H-cube MIDI. So this experiment goes to show that the scale-up using the H-Genie system becomes actually really quite easy, because you have to just multiply the conditions or maintain the same conditions and multiply the throughput by a factor of your choice, and that will approximately allow you to achieve your desired amount of throughput per day or per hour. So thank you very much for your attention. That would be all that I would have liked to talk about. And now we are going to move on to the questions and answers section. So if you have anything that you would like to discuss or ask, please feel free to type them into the comment section below, and we will discuss that. All right, so we have 2 questions by email that's come to us. So let me read them to you. Meanwhile, you can still think about your own questions. So the first one is, what is the maximum throughput of starting material for the H-cube and for the H-Genie system? Well, that always depends on your chemistry, because every starting material has a different molar mass, so it's quite difficult to determine and to predict. But I would say that for the H-Cube Pro, it's suitable for a couple of 100 milligrams to a couple grams per day. So again, it depends on the scale that you would like to achieve. But I would say the maximum throughput for the H-Cube Pro is 5 to 10 grams per day maximum, based on the size of your molecule. And for the H-Genie system, again, it depends on the starting material and on your chemistry that you're doing. But if you're doing a hydrogenation, of course, the Genie can do 1,000 milliliters per minute of hydrogen gas. If you convert that into moles, you get 45 millimoles per minute of hydrogen gas. And because the hydrogen gas needs to be in a little bit of an excess compared to the starting material, I would say that the 2-to-1 excess will be sufficient for most purposes, and that means about 20 to 25 millimoles per minute of material can be hydrogenated very easily. And then, of course, you have to do your own conversion into grams, because I don't know what kind of chemistry each user is going to do, but it's very easy. It's just a multiplication. For most chemists, it's going to be in the range of several kilograms per day. So the one experiment that we have done using this previous example, the methyl nitrobenzoate reduction, it was actually 5 to 6 kilograms per day. So that's the maximum capacity of the H-Genie. All right, so the other question by email was, can you do a multi-step synthesis by joining 2 instruments together? The answer is yes. It's actually very easy, because each of these reactor systems are modular. So that means you can rearrange them in several different orders. So you don't have to stick to just one particular arrangement. You can modify that. The order of the instruments can be modified, and therefore, if you've got multiple instruments, you can join them together to form a reaction line, and that allows you to do several different steps. So if you wish to do 2 different step synthesis, then instead of collecting, imagine you've got your flow line exiting your first flow reactor, and instead of collecting that into a suitable flask or vessel, you can join that line to enter your second reactor. And you can use a mixer and a second pump to pump the second reagent and mix them together with the mixture that exits your first reactor. You mix them together with a new reagent and inject it to the second reactor line, and that will perform the second step of the synthesis for you. And this can be done in a million different ways. There are lots of solutions and a lot of people who are actually doing that. So yeah, it's actually very easy to set up a system. It takes about 1 day of work to set up the system according to your needs. All right, we have a question in the chat as well. Have you found any leaching of the metal? For the heterogeneous catalyst, for example, palladium on carbon and platinum on carbon, we have never observed any leaching. So of course there are other special types of catalysts, for example, palladium-2. So if you oxidize the palladium to the palladium-2 plus state, oxidation state, then it becomes soluble in different solvents, and therefore it is possible that a slight leaching effect will be observed. But for our palladium-0 and platinum-0 filled cat cards, which are the most commonly used metals in hydrogenations, we have never had a problem with that. So the filters at the end of the cat cards and all of our catalyst columns will prevent that effect from happening. So that's not usually a problem. All right, we still have a couple of minutes left. So if you've got any questions, just please feel free to use the chat box. And meanwhile, while we are waiting for some more possible questions, let me mention our website, which is ThalesNano.com. And you can find really interesting chemical applications for all of our reactors. You can find descriptions of our reactors as well. And there are a lot of application notes for you to read involving and containing interesting chemistries. And you can also sign up for our newsletter. It's completely free of charge, so that you will be always informed about our future activities and also upcoming webinars. All right, so I cannot see any more questions coming. So I would like to thank you again for joining us today, and have a very nice rest of your day. And thank you for joining. So, goodbye.